So we're going to be going through the basics of an operational amplifier. We have finished all the applications of operational amplifiers, which will be inverting, non-inverting, summing amplifiers, voltage followers, and comparators. We've done all of that, so we're going to look at the basis of an op-amp now. Because we've heard of these names and whatnot, all of these symbols and whatnot will make more sense. So let's zoom in a wee bit. So some of this I would have had it in the original handout, no matter. All right, so the complex circuitry of an op-amp, of an operational amplifier, can be represented by what is called an equivalent circuit. An equivalent circuit is a theoretical circuit which is much simpler than the circuit it represents. So our equivalent circuit is basically what we have been using all this time in the topic, which is our two inputs. We have our non-inverting input, we have our inverting input, we have our output, and then we have our source voltages. That is everything we are usually concerned about. Now, this is what our op-amp looks like. It looks like a little spider. Honestly, it likes a little spider because it has 8 legs. We just probably need to go and get some claws, some teeth. All right, and put in a whole bunch of eyes and try to make it look like a spider, but no. All right, so what these legs or what all of these pins here represent, we have something called offset null and offset null. We are going to be touching that when we do logic gate. So I'm not going to explain what offset null is as yet. But if you look here, we can see we have our inverting input. We have our non-inverting input. So our inputs are both on one side. We have our negative source voltage, right? Our 8th pin, which is probably this pin here, right, is not used. So this pin can probably break and it's not going to affect the circuit whatsoever. Right? And many of the components that we have in electronics or computing, you're sure you realize they have all these ports with a whole bunch of pins in them. We've all noticed that. All right? But not all of these pins are usually active. It depends on where it is being plugged in, because each pin here represents a different component or a different connection. So here the 8th pin is not used, so this can break and come out, and it will not make a difference to your op-amp at all. All right, so that's the only one here we can sacrifice. We have our positive source voltage, and then we have our output. So this is actually all the things that we know regularly in op-amps. We know our inverting input, our non-inverting input, our source voltages, because an operational amplifier requires electricity to work. Right? If we do not apply electricity to our computer, it will not work. All the components we have, all the fancy circuitry and microelectronics makes no sense or is useless without a source voltage. Right? So the source voltage here is simply the power it needs to work. So here we're going to go through just a couple little small examples on how you use your op-amp. So if you want to know how to get your inputs and outputs, now this is using your calculations backwards. Sometimes we do not know how much power to put into our operational amplifier, but we know how much we will need. Right? We know we will need a certain amount of voltage being put out by our operational amplifier. So we could go now and determine how much we can put into our op-amp. And how do we do that? This is the backward working. Remember gain is equal to just VO over VI. And if I want to know my output voltage, it's going to be A by VI. If I want to know my input voltage, right, as in I want to know how much voltage I can put into my operational amplifier without it having shut down, it's going to be the reverse of this. It's going to be V0 over A. Really simple maths. So let's read here. If an op-amp with a plus or minus 9 volt power supply Oh, an op-amp with a 9 plus or minus 9 volt power supply. Why do we say plus or minus? Because all of these take alternating currents in them. So we have to consider 9 plus or minus volts. The maximum power output or the maximum voltage output will be plus or minus 9 volts. As in, when your output is more than your input, it is not going to work. All right, so the maximum voltage you can ever put out or you can take out of your operational amplifier is close to your source voltage. So this is us determining what voltage can we put into our amplifier so that it can amplify the signal and not shut down the system. All right, now the nice thing about operational amplifiers, when the voltage gets too high, it shuts down. It's not like a fuse, right? Remember for a fuse, when your current is too high, right? When your current is too high, that fuse is going to burn out, create a short circuit, and stop your current from flowing. But when this happens, we have to now go and replace, right, a component. For operational amplifiers, all it does is click, it shuts off, and you need to know and dial back your voltage. For those of you all, everybody here should iron. You all ever realize when you're using the iron, you hear it click and it turns off while using it?
Yeah.
Right? It turns off a very short time because it knows when it reaches a certain temperature, right? The components should not get any hotter than that. Imagine something like an iron. It's meant to get hotter, but we don't want our iron to reach 500 degrees and burn up our clothes, which we already do. How many people here, raise your hand, and I raise my hand too, has burnt their school pants and skirt? I am raising my hand, right? I can say I can raise my hand for this, right? I do, I have burnt my school shirt and pants, and my work pants too. All right, now that's when the temperature gets too high. All right, so what it does in a iron, there's a little component that is meant to shut off the power when it gets too high, and then when it cools back down, right, it reconnects the power supply. Wow, that is rain. You only hear any rain? I could barely hear myself.
Hello.
Yeah. All right. So same thing here for an operational amplifier. It can act as a switch, right? Or it can tell you when the power is getting too high, because if your input is too high, your output is going to be too high, right? And when your output is too high, our amplifier here shuts down. So back to the original topic at hand. So an operational amplifier with a 9-volt power supply will have an output of 9 volts. If there is a gain of 10 to the 5, then the maximum voltage input will be 90 microvolts. Now, how are we going to work that out? Get your calculators out. All right. So here, if we know that VI is equal to V naught over, okay, Jesso, hold on. Why are you doing that? Okay. V naught over A. So all we have to do here is find out V naught, which is 9 volts, because that's the maximum voltage that we can put out or take out of our amplifier, right? Because as soon as your output voltage crosses or is larger than your source voltage, it shuts down. So the maximum voltage here that it can put out is 9 volts. Divide by 10 to the 5. You're going to get 9 by 10 to the minus 5, or 90 microvolts. Wow. Yeah. All right, so that's how you are able to determine what your input voltage, what is your maximum input voltage, just by looking at what voltage we are running our op-amp with and the gain that our op-amp should have. Right, now remember the standard gain of an op-amp is 10 to the 5. That's your standard gain. All right, that's the gain that the op amp itself has, not what the resistors give us. Remember, that's a different amplifier gain. All right, when we have a gain of 10 to the 5, that is the gain that this little device here itself provides. When we have the other gain, that is usually when we have the feedback resistor coming in and all that stuff. But the gain of the device itself is 10 to the 5 or 10,000, 100,000. All right, so continue reading. So this is how you're able to determine what is the maximum voltage you can put into your amplifier. Just look at how much power you're running and look at what your gain is supposed to be, and you can work out how much power you can put into your circuit. So amplifiers, continue reading. Amplifiers have two inputs, right? We have an inverting input, we have a non-inverting input, which we've done, and we can have one or two or three or a few other inputs. All right, reading further down, transfer characteristics. A typical characteristic is shown below. Now, what characteristic means? We're looking at how our voltage in compares to our voltage out. There's no IV in this because the current is meant to be constant in a operational amplifier. The only thing that changes is your voltage. So there's a small range of AOB, so that is this area here. You see this area here, which is the area of AOB, where everybody behaves very nicely, where we can get our gain very accurately. This is our AOB section. Here we're going to get the output is proportional to the input, and we can actually get a gain here. Somebody recall, how do we get gradients again?
Changing X over changing Y.
I can't tell you go home, you're done home.
Changing Y over X.
Oh my God. Seriously, dude. Right. So gradient is Y over X. Let us see what the gradient of this line here is going to give us. The gradient here is Y, which is V naught, and the gradient here is your input resistance. Isn't the gain here, V naught over Vi, is going to give you your gain? V naught over Vi is your gain. So the gradient of the IV character of the characteristic of your operational amplifier also gives you your gain. Look at the number of ways we can find gain in these topics. You can look at the gradient of the line. You can compare your resistors. We can look at the resistors inside of the amplifier. All of these things tell us what the gain is. Or you can plot a graph, find the gradient of the slope, and you get your gain. Multiple ways to find the same thing in this topic. So continue reading. So we have this section here. This is where everything behaves very nicely and very predictably. Now, inputs outside of the source voltage. So that means when we reach the source voltage and we go up over the source voltage, right, what happens? We're going to get our amplifier flattening out, meaning the output voltage is not going to change. All right, this is what it means by it shuts down. It's no longer an amplifier. As an amplifier, it's no longer working. And let's read what's happening here. In inputs outside of the source voltage, Vs causes saturation. And when a transistor, which is what an operational amplifier is made up of, many transistors, right? So when a transistor is saturated, it acts like a short circuit. What is a short circuit again? Anybody? What is a short circuit?
Yes, I remember, but I can't remember at the same time.
Next. Anybody? What's a short circuit? Rohan, short circuit.
Miss, I think that when the current could be infinite.
Next.
Miss, a shortage of circuit?
A what?
I don't know.
I need to stand up in front of the school with a ruler for everyone all day when all they come back out of school. Here, take this. A short circuit, my dear wonderful children, is essentially
That's when the current not flowing
a gap in
properly.
your circuit.
Miss,
That is
that
no
one mean
no
shortage of
no
circuit.
no 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 no. This is what a short circuit is. A short circuit is a gap in your circuit. And if there's a gap in your wires, right? You know, these extra shame and all that because we did short circuit for mystery box in Form 5. Nah, boy.
That's like if your computer just coming on and off, on and off, on and off. It's a
Where the mute
short.
button for Jabari? I never used the mute button on you yet, you know.
Nah, don't beat up, don't beat up.
All right. So let's just finish up here. So what happens when you have a short circuit in a system? Your current is 0. It is not infinite. No, infinite is no. All right. Whenever you have a short circuit, that means there's a gap in the system, or there is basically no current flowing in your circuit. So that's how we say it shuts down. So that's why you never want to operate above your voltage saturation or saturation voltage, because your circuit will end up behaving like it's a short circuit. And short circuits mean that current is no longer flowing. So it's again turned off. It's not working at that time. I didn't say it's broken, it's just not working. Frequency response. Now, the voltage gain of an amplifier is fairly constant over most of the frequency range. It does fall off at low and high frequencies. Now, why are we speaking about frequencies? Because we again are using alternating currents, and an alternating current will have a frequency. Remember, frequency is 1 over periodic time. So all you have to do, and then you have multiple waves. So the frequency is 1 over periodic time. So our alternating current will have a frequency. But we can use this. Let's use the example of the most widely known amplifier that we have, a sound amplifier or microphone system. You all do know we get this really weird hum when the frequency is too low on a microphone. You ever notice that?
Nah, I don't think so. You know.
Yeah, you get this really, really low hum. All right, that's when frequencies are too low entering your amplifier. You get this really low hum that goes through your microphone. Okay, and then you have the next one when the frequency is too high, you end up getting the feedback and you end up getting these screechy loud sounds when the frequency is too high. Now, when the sound is too high, remember, loudness and frequency are two different things. When your frequency is too high, your amplifier does not work as well because of your energies. So what we have here for an amplifier, right, we have the middle range. There's a certain range here where everything works good. Everything is fine. We have optimal performance of our amplifier. But then we have the areas where the frequency is a little too low and then a little too high. And at these areas here, it's not going to work as well. We're going to get a rapid fall off, as in it's not going to have the same amount of gain, right? It's not going to work as well. So let's continue reading. A typical gain frequency curve. So this is our gain. These are our frequency, right? Is known as a Bode plot. So this curve here is known as a Bode plot and is shown below. So let's read our curve and see what we have. We have our frequency on our y-axis. We start at 0. We have our open loop gain, and then we have our, we did this number of 0.707. Anybody remember what number that is? How we get that number?
But that's the RMS value or something.
RMS, yes, the same thing happens. Why are we talking about the RMS? Because again, we're talking about an alternating current. We cannot just look at the maximum voltage in our alternating supply. What we do, we end up taking the RMS, which is going to give us our root mean square value, right? Which is the most optimal point of our voltage. So this is the values we take. We don't ever take the peak because the peak happens for very short time. But if you look here, right, the time it takes between RMS values, this is your V over root 2. All right, is what we're going to take. So we're going to look at here, what is your gain over root 2? So 0.707 is your gain over root of 2. And we're going to take the intercept between that that root mean gain and the frequency and the curve is going to give us two frequencies. We're going to get FL and we're going to get FH, where FL is your low frequency and your FH is your high frequency. Bandwidth is the range of frequencies. So this is the term you have to learn here. Bandwidth is the range of frequencies within the gain that does not fall below your root mean gain. And your root mean gain is simply your maximum gain divided by root of 2. And how do we calculate bandwidth? Bandwidth is just simply you find out what FL is, you find out what FH is, and you get the difference in your two values. Now, in our operational amplifiers, you are very, very, very rarely going to see your question looking like this. Your curve will very, very rarely look like this. Instead, we're going to get a curve looking like here, where you have a straight line going down. But it's the same thing. We just start with our frequency from 0 staff meeting on the 4th of February. All right, okay. All right, so what we have, did you all see that message when it came up? That I have staff
No.
meeting? Okay, so that doesn't show up either. All right. So we have our frequency curve here, and we have our amplifier. Now we have our open loop gain. This is our open loop gain, and we have our closed loop gain. Open loop gain is always greater than closed loop gain. What is open loop again? It is just V naught over VI. What is closed loop gain? Either for inverting or non-inverting, which is a little different. These two will be different for closed loop gain versus open loop gain. Two little different things. So you're going to have a higher gain. What you do, all you have to do is see where your gain line is, where your gain line intercepts with your AV over root 2. So you just have to find out. Suppose my maximum gain here was 0.8, not 0.8, 4,000. Then I'm going to read off my curve here at 4,000 over root of 2. We have some questions. We'll go through it and you'll see. All right, and you just find your intercept. Your intercept is going to start at 0, and then you're going to find your other curve. So we'll get our closed loop gain, and we don't do unity gain at this level, so I'm not really going to bring it into the topic. Now, frequency is usually in a log scale. What topic did we do with log scale again? From unit 1, anybody remember?
Not that much, I can't remember that.
Anybody remember that we did decibels, we had to use log scales?
Yes, that's like with the 000 111 like that.
No.
I know what you're talking
No, I
about.
don't remember.
That would intensity and thing.
Yep. That was when we did sound. Yeah.
Yeah.
Anyway, but for here, sometimes we get our frequencies in millions of hertz. And it makes no sense to go and plot 1 million or even by 10 to the 6. All right. What we do, we end up using log scales, and then you have to reconvert it when you're finished doing your calculations. But you'll see if we encounter any questions with the logs, we'll just do our calculations with it. So this is it for OpAmps. All right, no questions today. All right, everything else is here. So that is it for OpAmps. Next day, we will do what did I say next day? Next day we will do questions. So I did give you all 5 questions in the classroom. We will give them a start, all right, on the next day. And then that same day or right afterwards, we'll start logic gates. Again, we're waiting on timetable for school to open back up. You all are only coming out to see me for 8 sessions. All right, it's probably going to be half-day sessions, not 1 hour period, because there's no way we can do labs and stuff in 1 hour, or a 1 hour period like what we have online. All teaching will be done online. We only allowed 60 people on the compound at any given time, so that means we are going to have to run on a timetable as to when you all are coming back. So you're not going to be back out of school full-time whole day, all right? Or you might, I doubt. Yeah, the only people who have practicals are going to be back out of school. Remember, you come in full uniform, proper uniform at all times, proper belt, proper shoes, proper socks, proper hair. Guys, no earrings in the ears. Leave that for outside of school. I will be seizing earrings. All right. So wear your uniform properly. You're only in uniform for a few more months. So let's do this proper. All right. And I might speak to you all again as your form teacher before school opens on Monday. But that's it for here.